So because we are trying to understand like what's happening to like dipole moments and how different molecules can actually get like a dipole moment, let's look into this molecule, right? So what do you think? So there are two dipole moments, and dipole moment being just the distance times like the charge. What is going to be the net dipole moment of this molecule? So it's like a force, like I'm pulling in this direction by 5 Newton, and someone is pulling on that direction by 5 Newton. What's the net movement of, what's the net force?
0.
0, because they cancel out, right? What will happen to the dipole moment in here by the same logic?
0.
It's going to cancel out, because this is getting pulled in this direction, this is getting pulled in that direction, it's going to cancel out. But for H2O, now if you guys tell me it's bent, I'll take it, it's bent. Okay. Something like this. Okay. And this thing, being electronegative, is going to pull something like this. Now just imagine these as forces, right? So when you did physics, when do you remember like resolving force vectors and things like that? So if you have this, so this can be resolved as, so if this is a force, this could be, let's assume this is y, this is x, this becomes the fx, and this becomes the fy. Do you remember like this concept? If this was like theta angle, this became f cos theta, like this, and this becomes f sine theta? No?
Mm-hmm.
Okay, maybe something. But you don't have to remember the math. What I'm telling you is, can you imagine this as a sum of, or the vector sum of, this and this? Do you remember something of that sort that we did in physics? Like, this vector can be a vector sum of this and this. Okay? Let's assume I'm right. And let's go from that. So in this vector, this was the resolution. And when you have another vector coming like this was, so if this was another, so this was fx, and this one was fy. So you see, this fx, this is fy, this fx, which is in this direction, and this fx, which is in this direction, are going to cancel out, right? But these things in the y direction, they're in the same direction, so they're going to add up. So for this, which direction do you think there is a net dipole? So there was this dipole and this dipole, where is the net dipole? Up. So because of these two, you get a net dipole, which is up. I'm not going to ask you to calculate that net dipole or give me the direction, none of that. I'm just asking you to think about the resulting, so whether a compound is polar or non-polar. That's our goal. We are not here to find out the exact polarity, but this is not a polar, so this is a non-polar compound, and this is a polar compound. That's what I want you to just convince yourselves, okay? This becomes important. Why? Because H2O is really abundant in the solar system. It's really abundant. H2O, there's a lot of H2O in the solar system. Some of that H2O might be free, like in the oceans, lakes, rivers. Some of that H2O might be bound in minerals, in organisms. What's a human body made up of? It's 70% water, right? Why? And why are we 70%? Why are we not 70% alcohol? Because alcohol too is a polar covalent compound, right? Because if you see something like this, because of this electronegativity, there is a polarity towards this side. So alcohol is also a polar, but it's not that common. That's why. But there might be other very common things which are not polar, like CH4. What's the structure of CH4? Anyone remember from organic chemistry? Yeah, but what's that called? What's that shape called?
Is it like a?
It has a name. It's tetrahedral.
Oh, okay.
Remember? Right? So tetrahedral. So it's a regular tetrahedral. So you have carbon. I cannot draw this molecule properly so that you can actually see the structure, but we'll discuss about this. What I'm going to tell you to believe is there is an electronegativity difference that you don't have to believe that's there, but the difference is not that much, first of all, between carbon and hydrogen, and that is why they're doing like a covalent bond, right? But all these dipole moments, even if there was a dipole moment, cancels out by the similar logic in a 3D arrangement. We'll look into that. So since this dipole moment cancels out, this becomes a polar or a non-polar? There is no dipole moment because the dipole moments cancel out. So that makes it what? Polar or non-polar? Non-polar. So it is non-polar. Write down this like small thing. Like dissolves like. What does that mean? That means non-polar solutes will be or non-polar solvents will dissolve non-polar solutes, and polar solvents will dissolve polar solutes. Extremely important, and that is why the salts, which are ionic, which are polar in nature, like that's their nature, salts, they dissolve in water. They don't dissolve in a non-polar liquid like liquid methane, which exists on Titan. But for life, we need ions. We need the different kinds of ions. First, the 4 biomolecules that we have. So we have carbohydrates, we have lipids, we have proteins, and we have DNA. A lot of these are polar in nature. On top of that, there are other requirements of elements like sodium, potassium. They need to be dissolved. It's there in your system. That is, so your blood pressure is related to the amount of sodium intake. So you don't eat a lot of sodium or you're dehydrated, you feel horrible because your electrolytes, which are dissolved in water, which you're made up of, is getting wonky. This is important because when we talk about life on methane, life on Titan, that life will not be at least similar to what the life as we know it. Because life on Earth as we know it is water-based life.
But wouldn't it still be carbon form?
It could be because there's a lot of carbon available. So it should be like a lot of, so what all life forms that we have known till now have 2 things in common. First, they're all made up of carbon, and second, they all require water in some form. Okay, they are the 2 common things. So Carl Sagan called us like water chauvinists or carbon chauvinists, because we always, whenever we think about life, we think about carbon and water. It doesn't have to be like that. We don't know anything about the universe. We just know so little thing about our own universe, and our ignorance is staggering. So we don't know anything. Okay? that's why to just tell that this might not be, there will still be carbon based or not be carbon based, I don't know, it could be anything. But it's likely that if there is some form of like life on Titan, some strange form or some, I should not say strange, I should say dissimilar form of life on Titan, it's likely that they will be carbon based because there is so much carbon, it's availability. Like you use whatever you have, it might not be, it could be silicon based, who knows? Because we have a lot of silicon as well. And silicon and carbon, they're in the same period, in the same group, 14th group. And silicon just comes below carbon. So there's a property of carbon called catenation. It's like, so this carbon forms chains and all these kinds of bonds. It can form chains and rings and side chains and whatnot. Silica can also do that. Silicon can also do that. And that is why we have a lot of silicates on Earth. So we have a lot of different kinds of silicates. You have chain silicates, you have inosilicates, you have phyllosilicates. So not that much, as much as carbon. And that's why a whole branch of chemistry, called organic chemistry, is dedicated to the study of carbon and its compounds, except carbonates, bicarbonates, carbon monoxide and carbon dioxide. Those are not studied in organic chemistry, but there are like billions of compounds probably that carbon can make, maybe even more, who knows. There's no limit, like that's the thing. So yeah, we don't know, but this won't dissolve salts. That's a major thing that I want you guys to understand. That since this is a non-polar compound, this is not going to dissolve any salts. So if you put sodium chloride in it, nothing is going to happen. This basically is giving you a delta negative, delta positive, and this delta negative basically will stabilize the sodium plus that is there. Kind of think like that. So charged, anything that is producing charged, which is the ionic, is going to be stable in those kinds of solvents that also have a charged behavior or some kind of like a charge distribution. Okay. Now, there could be, so all these things could be happening. So CCl4 by the same logic is also non-polar. Okay, CH4, CCl4, these are non-polar. So please keep in mind, like dissolves like. So non-polar compounds will be soluble in CCl4. So anything that is non-polar, like sulfur, maybe. So sulfur will dissolve in a carbon disulfide. So like you have carbon dioxide, so there is this compound called carbon disulfide, so CS2, sulfur dissolves, probably in that. So non-polar things will get dissolved in non-polar solvents, and polar solutes will dissolve in polar solvents, okay? So that's that. Now, there could be interactions between different kinds of, these are also interactions, right? So there could be an ion-ion interaction or a dipole-dipole interactions. So all these kinds of like different interactions, I always forget the different, like there are 6 or 5 different kinds of interactions. Not that important as covalent ionic and metallic bonding, because these are not bonds, these are just attractions, right? So whenever you have like a sodium, so if you have an H2O, there a different so this anything, so HCl for example, so this is going to attract another molecule of HCl through ion-ion interactions, because this is forming like, sorry, a dipole-dipole interaction, because HCl is forming a dipole there. There's another HCl molecule that is also forming a dipole. So that is going to interact, and what's that interaction going to do? Make it more stable or less stable? Hmm? Why? You're right.
If there's an interaction between two different things, I would think that the relationship between them will be stable, more stable.
Yeah, that interaction has to be attractive. And you're right, I mean the Cl minus, this is going to be attracted to a different HCl. So imagine there's an H and Cl coming from this way. So this attracts. So because of this attraction, now you can say, oh, so this Cl can also interact with other Cl which is a negative that increases the energy. It can. But in general, nature doesn't want to fight. I mean, it wants to stabilize. No one wants to increase its energy. If there is a possibility of decreasing your energy and becoming more stable, generally, like, if I can be friends with you, why unnecessarily I pick you on your bad things? Because all of us have their good parts and bad parts, right? Why unnecessarily? So will I pick on your negatives and increase animosity? I will rather choose to look at your good part and be friends with you. So that it becomes more stable. It's not always true, but generally, this is what happens, okay? If there is a possibility of an attraction lowering down your energy, it does not. Now there is a very important attraction that exists, and it is called hydrogen bonding, okay?
Does that happen in water?
Yes.
Okay.
I'm today very reluctant to rub, like to erase the blackboard. Last time it went on, it led to like all these kinds of like, I don't know, I didn't like it, so I'm like trying very hard to like just fill up the board and like write less. So hydrogen bonding. So hydrogen bonding is basically an interaction, but it's an interaction between something and hydrogen, right? So it's an interaction between a hydrogen and a really electronegative element. And what's a really electronegative element? It's very subjective, but maybe a little bit in Cl. So an interaction between this and H. It's an interaction. And whenever you have an interaction, what is that going to do? Increase its stability or decrease its stability? Increase the stability, because it's an interaction between H, which is a less electronegative element. Please remember, there is no electropositive. Metals are not electropositive, they are less electronegative. Hydrogen bonding is an interaction between hydrogen, which is a less electronegative element, and a very high electronegative element. So this is basically the minuses, kind of, and this is the pluses. So you're again developing a minus and a plus. So whenever there is an attraction, the energy drops by that amount. If you have a stronger attraction, then more energy is getting dropped. So in here you have more attraction between F, O, or N. Which will be the highest attraction? F, O, or N? Fluorine, because it's the highest electronegative, right? So it's the highest electronegative, and that is why it is becoming more stable. So let me put up a question. So you have H2O as liquid. So this is group 16. So if you have H2O, you have H2S, and so forth. When the molecular weight, so molecular weight is increasing this way. I hope there is no doubt in that. So molecular weight is decreasing, increasing, right? So becoming more and more heavier. When things become more and more heavy, there is a type of interaction that increases. It's called van der Waals interaction. So bigger molecules will have more van der Waals interaction, and smaller molecules will have less van der Waals interaction. Also, when you have more surface area, you have more van der Waals interaction, and we have less surface area, you have less van der Waals interaction. So, if we are thinking about van der Waals first, let's look at van der Waals interaction first. So let's assume you have a pentane. I'm not showing the hydrogens. It will be something like this. So this is a pentane. This is a normal pentane, as we call it. And you can also have something like this, right? This is an isomer of pentane, which is called, this is 2,2-dimethylpropane, but you don't have to remember that if you don't. It's easy. If I get a chance, I will discuss this. But this has the same exact formula as this compound. The same. So that's, if you have the same, if you have the same molecular formula but different structures, they're called isomers of each other. So there are structural isomers, there are stereoisomers, organic geochemistry. Okay. These two, can someone take a guess? Which of these would have more boiling point? Now, can you guess which of, so pentane will have more boiling point, which is C5H12, versus if you have C10H22. Which of these will have more boiling point?
The C.
Why? It's just more mass. More, sorry?
You say more surface area for that?
Not. Let's bring the surface area to discussion on this one, because the molecular weight is the same. In here, the molecular weight is different and like considerably different. So when you have more molecular weight, in generally their boiling points will increase. So this will have more boiling points. It's more massive. That's it. More interaction, more availability of attraction and whatnot, more bonds, things like that. But in here, the molecular weights are same, so that we cannot think about that. But here you have to think about surface area. I'll give you a hint. Less surface area means less interaction. So first, let's find out which has less surface area. Which of these do you think has less surface? This one or this one?
The second one?
Why? How do you know? How many of you think this? There can be intuition too, and you don't have to explain your intuition. Intuitively, who thinks this has less surface area? What do you think? This or this? This. Why? Sphere is a very, interesting shape. Sphere has the least surface area for any given volume. For any given volume.